On November 12, 2025, astronomer Gianluca Masi, using the Virtual Telescope Project's instruments, directed his focus toward a faint smudge in the sky. This was comet C-2025 K1-ATLAS, a comet that had been discovered earlier in Chile by the ATLAS survey network. Masi anticipated a routine observation, perhaps a simple roundabout of a comet as it circled the Sun. However, what he saw next was far from ordinary. The comet, rather than smoothly gliding across the sky, appeared to be breaking apart, pieces of it splitting away in real time. The images from the night revealed a violent shattering, with the nucleus of the comet separating into several well-defined fragments. Each fragment left behind its own distinct cloud of gas and dust, a pattern that stood out in stark contrast to the usual diffuse, scattered breakup seen with comets. What was most striking, however, was the sharp and almost deliberate way these fragments drifted apart. The breakup wasn't the result of random chaos, but a well-structured, almost mechanical event. The brightest fragment had a plume of gas emanating from beneath it, not dissimilar to a spotlight, steady and persistent. While comets are known to fragment under the heat and pressure of the Sun, this was not the typical breakdown. Usually, comets disintegrate gradually over weeks or months, shedding layers of debris. K1's break was sudden and organized, and the speed and structure of the fragmentation were unlike anything that had been documented before. Most comets that pass too close to the Sun don't survive at all. K1, however, made it through perihelion, its closest approach to the Sun, which occurred at a perilously close distance of 0.334 astronomical units, a range close enough to vaporize many comets. But K1 did not shatter immediately upon the closest approach. It withstood the worst of the solar radiation and tidal forces and only began disintegrating once it was safely on its way back into space. This delay in its fragmentation puzzled scientists. Shouldn't the comet have broken apart during perihelion when it would have been under the most strain, or afterward if it had a strong enough structure? Instead, it fell apart after passing through what was supposedly the worst of the solar encounter. Why wait? The story doesn't end there. The behavior of this comet raised further questions when astronomers realized that K1-ATLAS wasn't the only unusual object to appear from the ATLAS survey network. In July of the same year, the third interstellar object to be detected, 3IATLAS, was confirmed as having entered the solar system. Both objects were discovered by the same survey network, with similar unusual behaviors, and this coincidence immediately raised the question of whether the two were somehow related.
Could K1, despite being classified as a typical long-period comet, in fact be another interstellar visitor, or even a fragment, a larger object that had entered our solar system earlier and broken apart before anyone could notice? What if the fragments of K1 were remnants of a more significant body, now arriving in pieces? The initial data from K1-ATLAS were intriguing, to say the least. As Gianluca Masi observed the comet's fragments on the 12th and 13th of November, the regularity and coherence of their breakup were unlike the scattered chaos typically seen in cometary disintegration. Even more curious, the plume of gas underneath the leading fragment suggested an active process was at work, as though the comet was venting pressure from within. These early observations, though incomplete, were already enough to hint that something unusual was unfolding. Within 24 hours of K1-ATLAS's fragmentation, astronomers tracking the comet made another startling observation. The fragments weren't just drifting apart as expected after the breakup, they were moving in ways that gravity alone couldn't explain. There were small accelerations, slight shifts in their trajectory that shouldn't have been there. Comets are known to deviate from pure gravitational paths due to the outgassing of their ices. As they approach the sun, the heat causes their ice to sublime, releasing gas that pushes against the comet's surface, creating a small but continuous force that alters its trajectory. However, in K1's case, the motion anomalies were more pronounced than usual, suggesting forces at play beyond what outgassing alone could explain. The behavior of interstellar objects had been documented before. For instance, in 2017, the first confirmed interstellar object, 1I Oumuamua, accelerated away from the Sun in a way that gravity alone couldn't entirely account for. Similarly, in 2019, 2I Borisov, the second confirmed interstellar object, showed some peculiarities in its motion. However, K1's motion seemed even stranger. Its acceleration didn't align with the expected pattern from outgassing alone. The fragments appeared to diverge in a way that suggested additional unexplained forces were at work. For scientists, this wasn't just another comet. The rapid separation of K1's fragments and their unexpected movements had begun to cause unease. The data was too inconsistent with known comet behavior. Usually, when a comet fractures, the pieces drift apart slowly, propelled by the residual rotation of the nucleus and gentle outgassing. K1, however, exhibited higher speeds and a more irregular divergence, and these movements occurred almost immediately after the fragmentation. The speeds at which these fragments separated, several meters per second, were too high to be explained by the passive separation process typically observed in cometary breakups.
While some might attribute this to asymmetric outgassing, where one fragment has an active jet and another doesn't, this theory doesn't fully account for the fragmentation pattern. The velocity of the fragments and the consistency of their acceleration over several days suggested that something more significant was pushing them, perhaps a more profound internal structure or energy release from within the comet itself. To put it in perspective, K1's movement wasn't just an anomaly in the speed of its fragments, it was in how those fragments diverged. They were not following the simple expected path based on their initial velocities or the sun's gravitational influence. The motion didn't make sense in the context of what scientists expected from a comet. When astronomers turned their spectrographs towards K1-ATLAS, they expected to see the usual chemical fingerprints of a comet. Carbon-based molecules such as C2 and CN radicals, which emit the characteristic blue-green glow that most comets display. However, what they found was surprising. Instead of the usual carbon-based emissions, there was a significant absence of these molecules, particularly carbon. In cometary science, the presence of carbon molecules is crucial. When a comet approaches the sun, the heat causes volatile compounds, like carbon dioxide, to sublimate. As the material breaks down, carbon monoxide, atomic carbon, and various organic compounds are released, each leaving a specific signature in the comet's coma. This is what gives comets their iconic colors and makes them visible from Earth. But in K1, this typical signature was almost absent. The carbon-based molecules that would usually dominate the spectrum were found in such low quantities that the expected cyan blue glow was missing. This anomaly was troubling. Carbon depletion is not unheard of in comets, but it's extremely rare. Only a few comets observed over decades of study have shown similar depletion, so when it appears, astronomers pay attention. What does carbon depletion mean? It indicates that K1's chemistry didn't match the standard cometary template. It could have formed in a colder region where carbon compounds froze differently, or perhaps it had been subjected to conditions that caused it to lose its carbon content before entering the inner solar system. Other explanations could suggest that K1's composition was different, with more rocky material and less ice, or that it had passed too close to the sun in its previous orbits, stripping away its volatile carbon over time. This anomaly raised more questions about K1's origins. Was it just an unusually composed comet from our Oort cloud? Or could it have come from elsewhere? Perhaps from another star system, where the chemical makeup of comets might be drastically different.
While most comets tend to exhibit a blue-green color due to carbon-based gases, K1's golden color hinted at a unique mix of materials that behaved differently when exposed to solar radiation. The comparison between K1-ATLAS and another interstellar object, 3I-ATLAS, became even more significant as new data emerged. While K1 exhibited a dramatic and organized fragmentation pattern, 3I-ATLAS had also exhibited unusual chemical properties, particularly an unusually high ratio of carbon dioxide to water, a stark contrast to typical comet compositions. These two objects, both discovered by the ATLAS Survey Network, exhibited strikingly similar behaviors, including unusual motions and abnormal chemical signatures. Could they have come from the same source? Were they fragments of a larger body that had broken apart in space long before they entered our solar system? The possibility that K1 and 3I-ATLAS were related seemed to grow stronger as more data came in. Both had displayed highly unusual chemical compositions. K1 had low carbon levels, and 3I-ATLAS showed an excess of carbon dioxide. Could these anomalies be indicative of a shared origin, perhaps from a common interstellar source? The theory was speculative, but it raised a crucial point. K1 and 3I-ATLAS exhibited behaviors that couldn't be easily explained by conventional comet science. The more scientists studied these objects, the more they began to wonder if what they were seeing wasn't just a coincidence, but rather a pattern. Could interstellar fragments be entering our solar system more often than previously thought? The narrative surrounding K1-ATLAS and 3I-ATLAS leads us to an intriguing hypothesis that challenges our current understanding of interstellar objects. Typically, interstellar objects are thought of as solitary travelers, objects ejected from their parent star systems and wandering the galaxy for millions of years before passing through our solar system. This is the model that has governed our thinking since the discovery of the first interstellar object, 1I Oumuamua, in 2017. It passed through the solar system on a hyperbolic trajectory, a visitor with no return. The same model applied to 2I Borisov, the second interstellar object, and to 3I-ATLAS, the third interstellar object. But what if this conventional picture is wrong? What if objects from beyond our solar system don't travel alone, but rather as fragments, debris from larger bodies that broke apart long before entering our detection range? The interstellar drift hypothesis suggests exactly this.
It proposes that when large bodies are ejected from their parent star systems, whether through gravitational interactions, planetary formation, or stellar encounters, they don't always remain intact. The forces of radiation pressure, tidal forces, and internal stresses can fragment a large object into many smaller pieces, which then disperse across space, carried by slightly different velocities, and spread over time. Over the course of thousands or millions of years, these fragments would gradually disperse across the galaxy, traveling through interstellar space until they eventually arrive in our solar system, often separated by years or even decades. Instead of a singular interstellar object passing through our system, we could be seeing streams of debris, remnants of larger bodies that shattered long ago, arriving as individual fragments over a much longer timeline. This hypothesis is gaining traction as the similarities between K1-ATLAS and 3I-ATLAS grow harder to ignore. Both objects exhibited unusual motion and chemical anomalies. Could they be fragments of the same parent body? If so, their shared behaviors and appearance might not be coincidental. Perhaps they are pieces of a disrupted body, one that broke apart far from the sun, and now the pieces are slowly making their way through our solar system, entering from different angles, separated by vast stretches of time. The problem, of course, is that the orbital data for these two objects don't exactly match. 3I-ATLAS followed a hyperbolic path with an eccentricity well above 1, clearly indicating it was interstellar.
K1, on the other hand, follows an elliptical orbit, typical of long-period comets originating from the Oort cloud. These two trajectories don't immediately suggest a shared origin. But, as some researchers point out, this is where the complexity of the hypothesis becomes more interesting. Could K1's orbit be misclassified due to the limited observational data we have? What if its eccentricity is actually slightly above 1, just barely interstellar, and the ambiguity in its trajectory has led it to being mistaken for an Oort cloud object? This idea opens new possibilities. If K1 and 3IATLAS are indeed related, then we may be witnessing not two isolated visitors, but fragments from the same larger object scattered across time and space. The object's trajectories might differ because of gravitational interactions with planets like Jupiter or the Sun itself. Such encounters could change the velocity of the fragments, causing some to fall into bound orbits like K1, while others like 3IATLAS gain enough speed to escape the Sun's gravity entirely. Simulations of interstellar debris fields suggest that if a large interstellar body disintegrated far beyond our reach of detection capabilities, perhaps 50 to 100 AU from the Sun, the resulting fragments would spread out over time, following slightly different velocities and paths. Over thousands or millions of years, this debris would begin to arrive at the inner solar system, with fragments appearing at various intervals spread across decades or even centuries. The appearance of K1 and 3IATLAS within months of each other might be the first clear evidence that we are seeing this type of stream, a collection of interstellar debris entering our solar system in waves rather than as isolated objects. As if the fragmentation of K1 Atlas and its strange behavior weren't enough to stoke the flames of curiosity, further investigation into archival data has uncovered yet more peculiarities. Between 2022 and 2024, the Atlas Survey Network logged a series of faint transient detections in regions of space that would later align with K1's path. These were weak signals, too faint to be confirmed at the time, but upon closer examination, they seem to suggest the possible presence of K1, or more likely, fragments of a larger object long before K1 itself brightened enough to be detected. The objects detected in these early surveys were too faint and too brief to be classified at the time. They appeared as ghosts in the data, transient detections that could have been caused by any number of factors: cosmic rays, satellite glints, or processing artifacts. These ghost signals were dismissed as inconclusive. However, when astronomers revisited these logs after K1's discovery, they noticed an intriguing pattern. These faint objects appeared to follow trajectories that were closely aligned with K1's, and when extrapolated backward, they seemed to trace a path that was nearly identical to the one K1 would take when it was first detected in May 2025. If these signals represent early glimpses of K1 before it became visible, they could provide an important piece of the puzzle. More interestingly, these ghosts might not have been K1 itself, but other fragments, pieces that passed through our detection range unnoticed, too faint to be confirmed, yet still part of the same larger cosmic structure. K1 Atlas's fragmentation has led scientists to explore 3 different models that might explain its peculiar behavior. The first model is based on the idea of a rubble pile, a common structure for many comets. In this view, K1's nucleus was never a solid, cohesive body, but rather a loose collection of smaller particles and chunks of rock held together only weakly by gravity and frozen ice. When subjected to solar heat, the ice sublimates, causing the structure to weaken and the fragments to break apart.
This model fits some aspects of K1's behavior. The comet broke apart after its close approach to the Sun, and the separation speeds of the fragments were consistent with those seen in other rubble pile comets. However, the rapid fragmentation and the organization of the pieces challenged this model. If K1 was a rubble pile, why did it fragment in such an organized way, with the pieces aligning in a near-linear pattern? Why did one fragment exhibit such a persistent and directed plume of gas?
The second model proposes a monolithic but brittle body. In this model, K1's nucleus is a single, solid mass, like an asteroid, but fragile under the stresses of solar heating. The structure could fracture along planes of weakness when it was exposed to extreme heat, creating clean breaks and well-defined fragments. This model better explains the linear fragmentation pattern and the directed plume of gas from one of the fragments. However, the rapid fragmentation and the multiple fragments suggest that K1's material wasn't strong enough to support this model either. The third model involves an exotic composition. This hypothesis suggests that K1's nucleus contains materials we don't typically see in solar system comets, such as high concentrations of carbon dioxide or other volatile substances. If K1 originated in another star system, it might have formed under different conditions, and its chemistry could differ from anything we have encountered before in our own solar system. This composition could explain the carbon depletion, the unusual motion, and the organized fragmentation pattern. The investigation into K1's unusual behavior doesn't stop with its fragmentation and motion. One of the most perplexing aspects of the comet's disintegration is the persistent jet that has been emanating from one of its fragments. Unlike the brief bursts of gas typically seen in comets, K1's plume has continued to emit gas and dust for over 36 hours, creating a narrow, steady beam that extends outward into space. This kind of sustained emission is far from normal. Under typical circumstances, when a comet gets close to the Sun, heat causes the volatile ice on its surface to sublimate. As the ice turns into gas, it escapes, often carrying dust particles along with it, forming a visible plume. The intensity of this emission usually decreases as the comet moves farther from the Sun, and the sublimation process slows down. However, K1's emission appears to have been far stronger and longer lasting than expected. The structure of the plume itself is unusual too. It's much more focused and columnated, resembling a controlled jet rather than the diffuse, irregular shape typically seen in cometary outgassing.
To put the scale into perspective, if the plume is ejecting material at around 500 meters per second, a typical speed for sublimating water ice, and the mass loss rate is approximately 1 kilogram per second, the resulting thrust on the fragment would be about 500 newtons. This amount of force would be enough to cause measurable acceleration, even on a fragment weighing millions of kilograms. While the acceleration is relatively small by everyday standards, over time, it adds up, leading to the observed motion anomalies. This kind of emission is usually associated with comets that are still close to the Sun, where heat provides enough energy to drive significant outgassing. But K1's fragment is now moving farther from the Sun, and it is cooling down, receiving less solar energy. Despite this, the plume persists. This raises the possibility that the fragment still holds internal heat from its close perihelion passage, which is slowly being released. Ice is a poor thermal conductor, so heat absorbed by the surface during the comet's close approach to the Sun can take days to reach deeper layers, where it continues to drive sublimation. Alternatively, there may be some other mechanism at work, one that is providing additional energy to sustain the emission beyond what solar heating can offer. Could there be internal structural features, such as cavities or fractures, that trap gas and allow it to escape in a more energetic form once the pressure builds up inside? This kind of internal venting could explain the persistence and strength of the plume. What does all this mean in the broader context of interstellar objects? The strange behaviors of K1-ATLAS and 3IATLAS have led to a hypothesis that proposes interstellar objects may not travel alone, but rather as fragments of much larger bodies that have been broken apart long before they entered our solar system. The traditional view of interstellar objects is that they are solitary visitors, ejected from their parent star systems millions of years ago and wandering the galaxy until they eventually pass through our solar system. But this view might be too simplistic. According to the interstellar drift hypothesis, large interstellar bodies can fragment while still near their parent stars, with the resulting fragments dispersed across space and time.
These fragments travel on different trajectories, spread out over years or even centuries, eventually arriving in our solar system at various times. In this light, K1 and 3I/ATLAS could be pieces of a larger body that broke apart long before either fragment entered our detection range. If this is the case, their unusual motion and chemical signatures might not be coincidental, but rather the result of their shared origin. Both objects were discovered by the same survey network, both showed unusual behaviors, and both arrived within a few months of each other. This clustering of events raises the possibility that interstellar fragments might arrive in streams, not as isolated incidents, but as part of a larger pattern. It's worth noting that the data supporting this hypothesis is indirect and speculative. While the orbital data for K1 and 3I/ATLAS don't perfectly align, the fact that both objects exhibit similar anomalies, unusual motion, fragmentation patterns, and chemical compositions, suggests that there might be a larger story at play. Could K1 and 3I/ATLAS be pieces of the same shattered parent body, arriving separately in our solar system over a span of months or years? The question of what K1/ATLAS really is has become central to understanding its strange behavior. Scientists have proposed three main models to explain the comet's unusual fragmentation and motion. Rubble pile model. The first model treats K1 as a rubble pile, a loose aggregate of small chunks of material, held together weakly by gravity. In this view, the comet would be highly fragile, with layers of material that could break apart easily when exposed to solar heating. This is the most common assumption for comets. When the ice sublimates, the structure weakens and the fragments are released. While this model explains the comet's rapid fragmentation, it doesn't fully account for the organized pattern of the fragments or the motion anomalies observed. The uniformity and speed of the separation suggest that K1's structure may not be as weak as this model would suggest. Monolithic but brittle model. The second model proposes that K1 was a solid body, but one that was brittle and prone to fracture under stress. This model could explain the organized breakup pattern, as K1's internal structure might have contained planes of weakness, allowing it to break apart along these lines when subjected to solar heating. This model fits better with the regularity of the fragmentation and the directional plume observed under one of the fragments. However, it doesn't fully explain the chemical anomalies or the motion of the fragments, which suggest that K1's internal composition was more complex. Exotic composition model. The third model suggests that K1's composition is fundamentally different from typical comets. Perhaps it contains rare ice mixtures or high levels of carbon dioxide or carbon monoxide, which sublimate at higher temperatures and could drive faster outgassing. This model accounts for the carbon depletion observed in K1, as well as the motion anomalies and the organization of the fragments. If K1 originated in a different star system, its composition could have been altered by radiation or other environmental factors, making it behave differently from comets that formed in our solar system.
While the scientific community remains focused on natural explanations for K1's unusual behavior, a few researchers have proposed more speculative ideas, suggesting that the oddities observed in K1 might not be the result of natural processes at all. Could K1 be an artificial object, a probe, or a piece of technology sent by an advanced civilization? This theory posits that the organized fragmentation pattern, the persistent jets of gas, and the unusual chemical composition might be the result of engineered systems rather than natural fragmentation. Such claims are highly speculative and not widely accepted within the scientific community. However, the idea of interstellar probes or beacons sent by alien civilizations has been raised before, particularly in the case of 3I-ATLAS. Some researchers have pointed to the high nickel content detected in 3I-ATLAS, suggesting that the object might be made of processed materials rather than natural rock. The idea is that K1, with its strange fragmentation and motion, might be exhibiting similar behaviors to what we would expect from a self-disassembling probe. While this theory is far from proven, it raises interesting questions about how we interpret the data we collect. Could it be that some of the objects we are observing are not natural at all, but are instead the remnants of alien technology? As we continue to piece together the puzzle of K1-ATLAS's behavior, it's clear that the object's unusual properties are challenging our existing models of cometary science. But what do we know for certain so far? The evidence that has emerged from the fragmentation event and subsequent observations suggests several key points. Unusual fragmentation. K1-ATLAS didn't fragment in the typical chaotic way most comets do. Instead, its pieces were released in an organized, linear pattern, which is rare for comets that break apart. The fragmentation didn't happen gradually, and it wasn't random. It appeared to occur along pre-existing structural weaknesses, with the pieces following a pattern that suggested an internal structure rather than a loose collection of debris. This challenges the common assumption that comets are just fragile, loosely bound collections of ice and dust. Motion anomalies. After the breakup, the fragments began to move in ways that gravity alone couldn't explain. While it's normal for comets to experience some motion anomalies due to outgassing, K1's fragments diverged at speeds that were inconsistent with simple outgassing. This suggests that something more than solar heating is driving the acceleration, something internal to the comet itself. The fragments didn't just drift apart slowly, they moved faster and in different directions than expected, which makes the situation even more perplexing. Chemical anomalies. The spectroscopic data from K1-ATLAS revealed an unusual lack of carbon-based molecules that are typically abundant in comets.
Carbon depletion isn't unheard of, but it's rare enough to raise questions. The comet's chemistry was also different from what we'd expect based on its classification as an Oort cloud object. This suggests that K1 might not have originated from the same conditions that produce typical solar system comets, or that it has undergone a series of processes that have altered its chemistry. Potential interstellar origin. The behavior of K1-ATLAS bears a striking resemblance to 3I-ATLAS, the third interstellar object detected in our solar system. Both objects share similar chemical and motion anomalies, and both were discovered within months of each other. The possibility that K1 and 3I-ATLAS are fragments of a single parent body scattered across space and time is an intriguing hypothesis. If this is true, K1's fragmentation and unusual motion could be the result of the object's interaction with forces far beyond the Sun's gravitational pull, possibly originating from another star system. The strange behavior of K1-ATLAS, combined with the discovery of other interstellar objects, has pushed the boundaries of cometary science. The traditional models of comet formation and behavior are being tested, and the results are suggesting that our understanding of these cosmic travelers may need to be updated. If K1-ATLAS is indeed part of a larger interstellar debris field, as the drift hypothesis suggests, then we may be seeing only the beginning of a new era in cometary research. Objects like K1 may be more common than we thought, and our detection methods may need to evolve to identify these interstellar visitors earlier before they fragment and create the kinds of anomalies we've seen with K1 and 3I-ATLAS. The key to understanding these objects lies in developing more advanced models that can account for the unique behaviors observed in K1 and 3I-ATLAS. As telescopes improve and our observational capabilities increase, we will be able to track more interstellar objects as they pass through our solar system. Perhaps in the future, we will begin to see patterns emerge, not just from individual objects, but from entire streams of interstellar debris. The questions raised by K1-ATLAS and 3I-ATLAS are not likely to be answered easily. But the growing body of data is pushing us toward a deeper understanding of interstellar objects and their role in our solar system. While it's still uncertain whether K1-ATLAS and 3I-ATLAS are related, or whether they are truly interstellar in origin, one thing is clear: we are living in an era of discovery where new questions are arising faster than old ones can be resolved. The idea that interstellar objects may not be singular visitors, but part of a larger cosmic pattern, challenges the way we think about the universe. It opens up new possibilities for research and exploration, not only of comets, but of the broader processes that govern the movement of material through the galaxy.
As we continue to track K1's fragments and analyze the data from 3I-ATLAS and other interstellar visitors, we are learning that the solar system is far more dynamic and interconnected with the wider galaxy than we once thought. In the coming years, as our understanding of interstellar objects evolves, we may find that objects like K1-ATLAS are not anomalies at all, but part of a broader, ongoing process that we are just beginning to comprehend. The universe, it seems, has a lot more surprises in store for us than we've been able to predict. As we explore the mysteries of K1-ATLAS, 3I-ATLAS, and other interstellar objects, it's important to remember that we are on the cusp of a new chapter in astronomical discovery. The questions raised by these objects are prompting us to rethink not only our understanding of comets, but also our broader approach to studying the cosmos. The traditional categories we've relied on, comets from the Oort cloud, asteroids from the asteroid belt, and stars in our galaxy, are increasingly being challenged by new data that reveals the complexity of interstellar material entering our solar system. One of the key takeaways from K1's unusual behavior is that our current models of cometary science may be too simplistic. We often treat comets as fragile, predictable objects that obey the laws of physics as we understand them. But with K1-ATLAS, we've seen evidence of something more. A comet can be far more complex, with internal structures and behaviors that defy easy classification. This is not just a question of a comet breaking apart under the sun's heat, but of how these objects behave when they've been subjected to conditions we don't yet fully understand. The possibility that interstellar objects may arrive in streams rather than as solitary travelers opens up a whole new realm of exploration. If K1 and 3I-ATLAS are indeed fragments of a larger object, then they represent only a small part of a much bigger picture. Future research may reveal more pieces of this cosmic puzzle, and as our ability to detect faint and distant objects improves, we might find that these visitors from beyond our solar system are more common than we initially thought. The idea of interstellar debris streaming into our solar system is not just an interesting hypothesis. It has profound implications for our understanding of planetary formation and the processes that shape star systems. If large interstellar bodies break apart before reaching our detection range, scattering fragments across space, we might be witnessing the remnants of ancient planetary systems, systems that existed long before our sun was born. These fragments could be pieces of long-lost worlds, carrying with them the stories of their creation and destruction. The study of such objects could reveal new insights into how planets form, evolve, and ultimately break apart.
If we're seeing fragments of objects from other star systems, it might be possible to learn more about the environments in which these objects originated, their chemical compositions, and the forces that acted upon them during their travels through space. The question of how such fragments behave when they enter our solar system is equally important. If they are not simply passing through, but instead forming a continuous stream of interstellar material, we might need to reconsider the role these objects play in the larger picture of our solar system's evolution. Are these objects simply passing through, or could they be influencing the dynamics of our own planetary system in ways we have not yet understood? As we venture further into the study of interstellar objects, the role of advanced technology in shaping our understanding cannot be overstated. The rapid advancements in telescope technology, especially with instruments like the James Webb Space Telescope, have given astronomers the ability to peer deeper into space than ever before. With greater sensitivity and precision, these tools allow us to detect and analyze objects that were once invisible, opening up new avenues for research and discovery. Comet K1 Atlas's strange behavior, combined with its chemical anomalies and fragmentation patterns, is a case study in how new technology is revealing the mysteries of the cosmos. It's not just the size or brightness of these objects that matters, it's the way they behave, the subtle details that emerge when we can observe them with the precision offered by modern instruments. These discoveries, while unexpected, offer an opportunity to refine our models of cometary and planetary science, forcing us to adjust our assumptions and embrace new possibilities. Looking ahead, we can expect even more exciting revelations as technology continues to evolve. As telescopes become more powerful, we'll be able to detect even fainter objects and study them in greater detail. The increased resolution and sensitivity of instruments like JWST will likely uncover more objects like K1 and 3IATLAS, challenging our understanding of what's normal in the universe and pushing us to think outside the boundaries of current scientific paradigms. K1 Atlas and 3I Atlas are more than just anomalies. They are harbingers of a new era in space exploration and scientific discovery. These objects have forced us to rethink the very nature of comets, interstellar objects, and the broader dynamics of our solar system. The mysteries they present are not just puzzles to be solved, they are invitations to expand our understanding of the universe and to challenge the assumptions we've made about the objects that pass through our solar system. As we continue to study these objects and others like them, we will undoubtedly encounter more strange phenomena that push the boundaries of our knowledge.
Whether they are fragments from a larger interstellar body, remnants of ancient planetary systems, or something entirely different, these objects are teaching us that the universe is far stranger and more complex than we ever imagined. The implications of these discoveries are vast. Not only are we learning more about the specific objects that have entered our solar system, but we are also gaining new insights into the processes that govern the evolution of star systems and the interactions between different stellar environments. The study of K1 Atlas and 3I Atlas is just the beginning of a new chapter in our exploration of the cosmos. And as we continue to gather data, refine our models, and develop new technologies, we will undoubtedly uncover even more profound mysteries waiting to be discovered. In conclusion, the story of K1 Atlas is far from over. The questions it raises about the nature of comets, interstellar objects, and planetary formation will continue to drive research for years to come. As new observations are made, new theories will emerge, and our understanding of these objects will evolve. Whether K1 is simply an unusual comet or a fragment of something much larger, it has already left an indelible mark on the field of astronomy. In the future, as we explore more interstellar visitors, we may begin to see patterns emerge. Objects like K1 and 3I Atlas may not be rare exceptions, but rather the first signs of a larger ongoing phenomenon. The universe is full of surprises, and as our technology improves and our understanding deepens, we will undoubtedly uncover even more wonders from beyond the stars. As we delve deeper into the mystery of K1 Atlas, the bigger question remains, are we witnessing isolated events, or is something more systematic occurring? The increasing number of interstellar objects detected in our solar system raises the possibility that we are not just seeing one-off visitors, but part of a broader pattern. Interstellar objects are rare, but the more we observe, the more we realize that our detection capabilities have only just scratched the surface. For centuries, we've believed that objects like K1 and 3I Atlas were anomalies, rare wanderers passing through our solar system. But what if these objects are part of a larger stream of debris from other star systems? The idea that we are witnessing a cosmic rain of fragments constantly passing through our solar system challenges our previous assumptions. As our observational technologies improve, it's becoming increasingly likely that we will detect more of these objects in the coming years. The new generation of space telescopes, such as the James Webb Space Telescope, will give us the tools to look deeper into the far reaches of the solar system. This improved sensitivity will allow us to identify smaller, fainter interstellar objects that we previously missed.
The fact that two such objects, K1 and 3IATLAS, were discovered within months of each other suggests that interstellar visitors may not be as rare as we once thought. These objects may not be outliers, but part of a regular, ongoing phenomenon. If this is true, we will need to reconsider how we study objects entering our solar system. Instead of treating them as rare exceptions, we might begin to see them as part of a routine pattern that occurs more frequently than anticipated. The discovery of objects like K1-ATLAS and 3I-ATLAS invites us to reconsider the processes that shape planetary systems. If these objects are part of streams of interstellar debris, we may be witnessing remnants of ancient planetary systems that existed around other stars. These interstellar fragments could hold clues about the formation and evolution of planetary systems, offering us a glimpse into the processes that shape stars and planets in different environments. The chemistry and structure of K1-ATLAS in particular suggests that the materials in these interstellar objects may have formed under conditions vastly different from those in our solar system. For example, the carbon depletion observed in K1 and the unusual chemical signatures found in 3I-ATLAS indicate that these objects may have been exposed to different stellar environments, possibly forming around stars with different temperatures, radiation, and chemical compositions. If K1 and 3I-ATLAS are indeed fragments of larger bodies that broke apart long before entering our solar system, they might also provide insights into how planets and stars interact with their environment. The fact that these objects exhibit such strange behaviors, such as unusual fragmentation, unexpected motion, and chemical anomalies, could tell us something about the processes that govern the formation and destruction of planetary bodies in other star systems. As we continue to study K1-ATLAS and other interstellar objects, it's clear that traditional methods of comet and asteroid science are being pushed to their limits. These objects don't fit neatly into our existing models, and we may need to develop new approaches to study them effectively. One of the biggest challenges is understanding the behavior of these objects after they enter our solar system. K1-ATLAS, for example, exhibited an unusual fragmentation pattern that seemed to suggest internal structure rather than the typical chaotic breakups seen in most comets. Understanding why K1 fragmented the way it did will require new models of cometary behavior, models that take into account the possibility of interstellar material being exposed to different environmental conditions during its journey through space. Another challenge is accounting for the motion anomalies observed in these objects. The unusual accelerations and trajectories of K1 and 3I-ATLAS suggest that we may need to rethink how we understand cometary motion. While we know that comets are affected by outgassing, the behavior observed in these objects goes beyond what we can explain with traditional models. This opens up the possibility that some of these objects are not behaving like typical comets at all, and that we may need to incorporate new physics into our models of cometary motion. The future of interstellar object research looks incredibly promising. As our observational tools improve and our understanding of these objects evolves, we will likely uncover even more anomalies and unexpected behaviors. The study of K1-ATLAS and 3I-ATLAS has already opened the door to new possibilities in our understanding of the universe, and it's likely that future discoveries will only expand on this.
In the coming years, as our technology continues to improve, we will be able to detect even more interstellar objects passing through our solar system. These objects will provide a wealth of data that will help us refine our models of cometary science and planetary formation. Additionally, as we gain a better understanding of these objects, we may also gain insights into the processes that govern the dynamics of our solar system and the evolution of planetary systems in other star systems. For now, the mystery of K1-ATLAS and 3I-ATLAS remains unsolved. But as we continue to gather data and improve our models, we may be able to answer the questions that have been raised by these remarkable objects. Are they simply rare exceptions, or are they part of a larger, more systematic phenomenon? Are they fragments of ancient planetary systems, or are they something entirely different? The answers to these questions may take years or even decades to uncover. But one thing is certain, the study of interstellar objects is just beginning, and the discoveries we make in the coming years will reshape our understanding of the universe. As the study of K1-ATLAS and 3I-ATLAS continues, the cosmic puzzle they present grows ever more intricate. Each new piece of data adds complexity to the picture, forcing us to reconsider our assumptions and question the boundaries of our knowledge. These objects may be pieces of a larger cosmic puzzle, fragments of ancient, distant bodies that have traveled through the galaxy and now make their way into our solar system. Their behavior and composition challenge our understanding of comets, asteroids, and the very formation of planetary systems. And as we continue to study these objects, we may find that they offer us glimpses into processes and environments that are completely alien to our own. In the end, the story of K1-ATLAS and 3I-ATLAS is more than just a tale of two strange comets. It's a reminder that the universe is vast, unpredictable, and filled with surprises. What we thought we knew about comets, asteroids, and interstellar objects is just the beginning.
The mysteries of the cosmos continue to unfold, and with each new discovery, we are reminded of just how much there is still to learn. One of the most thought-provoking aspects of studying K1-ATLAS and 3I-ATLAS is the realization that we might not be seeing an isolated event, but rather the beginning of a new trend in the detection of interstellar visitors. These two objects, discovered just months apart, have raised crucial questions about how often we encounter interstellar material in our solar system. If the unusual behaviors exhibited by these objects are not anomalies, but part of a larger pattern, then interstellar objects may be more common than we ever imagined. For decades, scientists have speculated about the possibility of interstellar objects entering our solar system. Until recently, the detection of such objects was exceedingly rare. But with the confirmation of 1I/Oumuamua in 2017, followed by 2I/Borisov in 2019, and now K1-ATLAS and 3I-ATLAS in 2025, the frequency of these discoveries is starting to increase. This suggests that our solar system might be regularly intersected by debris from other star systems, much more often than our past observations have suggested. This growing recognition prompts new questions about the nature of these interstellar visitors. Are we simply observing the remnants of long-destroyed planetary systems? Are these objects harbingers of a greater cosmic process, a steady stream of material traveling through in the galaxy? Or do we only happen to be seeing a few stray pieces? The possibility that interstellar objects may be coming to us as part of an ongoing debris field raises significant implications. It suggests that our solar system is far more permeable to external influences than we once realized. If objects from other star systems are arriving more frequently, the study of these interstellar visitors could provide us with invaluable insights into the composition of other stars, planets, and even the conditions necessary for life to arise in the galaxy.
As we continue to detect more interstellar objects, the question becomes, what patterns will emerge? The discovery of K1-ATLAS and 3I-ATLAS within a few months of each other could be a sign that we are entering a phase where the arrival of such objects is more common than previously thought. Given the current pace of discoveries, astronomers are beginning to ask whether we will soon witness regular, predictable encounters with interstellar debris. Current models of solar system dynamics were built with the assumption that objects from other stars are rare, with only a handful of interstellar visitors arriving over millennia. But as more objects are discovered, this assumption is being challenged. Could we be entering a time where these encounters happen with greater regularity?
With improved technology and more sensitive instruments, the rate of detection of these objects is likely to increase, providing astronomers with a clearer picture of just how often interstellar material enters our solar system. It's still too early to predict whether interstellar objects will become a common phenomenon, but the increasing frequency of discoveries, along with the bizarre behaviors exhibited by K1-ATLAS and 3I-ATLAS, is prompting scientists to rethink their expectations. The universe, it seems, is far more interconnected and dynamic than we initially realized. What we once thought were rare occurrences may in fact be part of an ongoing cosmic process that we are only beginning to understand. The study of interstellar objects like K1-ATLAS and 3I-ATLAS isn't just about tracking strange visitors to our solar system. It also has profound implications for how we think about the formation of our solar system and others like it. The anomalies observed in these objects, particularly their unusual chemical signatures and behavior, suggest that there may be other processes at work in the formation of planetary systems than we have previously considered. For example, the carbon depletion observed in K1-ATLAS raises questions about how comets form and evolve in other star systems. Could the environment in which a comet forms play a larger role in determining its chemistry than we have previously thought? Is it possible that the conditions in other parts of the galaxy lead to the creation of objects with chemical compositions vastly different from those in our solar system? Similarly, the organized fragmentation observed in K1-ATLAS challenges our understanding of cometary structure. While many comets are thought to be loose aggregates of material held together by gravity and ice, the behavior of K1 suggests that its structure may have been more complex, with internal divisions or planes of weakness. This could point to new processes in the formation of comets and the materials that make up their nuclei. The study of K1 and other interstellar objects may reveal previously unknown details about the way comets and potentially entire planetary systems are built. Looking to the future, the study of interstellar objects like K1-ATLAS and 3I-ATLAS will likely play a crucial role in expanding our understanding of the universe. As our technology continues to improve, astronomers will be able to track more interstellar visitors with greater precision. The ability to detect smaller, fainter objects will be key to uncovering patterns in the behavior of these objects, as well as understanding the broader dynamics of interstellar material in our solar system. The increasing frequency of interstellar object discoveries also presents an opportunity to refine our models of solar system dynamics. The more we observe, the more we realize that these objects could provide valuable clues about the origins of our solar system and others like it.
The unique chemical compositions, motions, and fragmentation patterns of objects like K1-ATLAS offer a rare glimpse into the forces that shape planetary systems in distant star systems, providing a new perspective on the formation and evolution of our own solar system. In the coming years, as our technology becomes more advanced and our understanding of these objects deepens, we may find that the study of interstellar objects is key to unlocking many of the mysteries of the universe. These objects, once thought to be rare and unpredictable, may become a central focus of astronomical research, offering new insights into the nature of the cosmos and our place within it. The study of K1-ATLAS, 3I-ATLAS, and other interstellar objects is pushing the boundaries of what we know about the universe. These objects challenge our assumptions, force us to reconsider our models, and expand our understanding of the cosmos. While the answers to the questions they raise may take years or even decades to uncover, one thing is certain: the universe is far stranger and more complex than we ever imagined. As we continue to study these objects, we're reminded that nature has a way of surprising us. Whether these interstellar visitors are fragments of ancient bodies, remnants of destroyed planetary systems, or something else entirely, they are forcing us to confront the limits of our knowledge. And as our observational tools become more advanced, we will no doubt encounter more surprises, objects that challenge our understanding of the universe and inspire us to think more deeply about our place in the cosmos. In the end, K1-ATLAS and 3I-ATLAS are just the beginning of what promises to be an exciting new chapter in the study of interstellar objects. They remind us that there is always more to discover, that the universe is full of mysteries waiting to be solved, and that our journey of exploration is only just beginning. K1-ATLAS has raised fundamental questions not only about the nature of comets, but also about how we understand the movement of celestial objects within our solar system. The traditional view of comets as fragile, predictable bodies that obey the laws of physics without straying too far from expected patterns is being questioned. The behavior of K1, its unusual fragmentation, the linear arrangement of its fragments, and the peculiar motion anomalies suggest that comets are not as predictable as once thought. Comets have been studied for centuries, but our understanding of their behavior has been limited to a small sample of well-understood examples. The discovery of K1 has forced scientists to expand their models, challenging long-held assumptions about how comets form, how they behave when subjected to the sun's heat, and what happens when they break apart. K1's unusual fragmentation, which occurred after perihelion, the closest approach to the Sun, raises questions about the stress thresholds of cometary nuclei.
Most comets are expected to break apart when they get closest to the Sun, subjected to the greatest heat and tidal forces. Yet K1's fragmentation occurred days after its closest approach, when the comet should have been relatively stable. This suggests that we may be missing critical factors that influence cometary breakup. Could it be that comets do not simply break apart under the heat of the Sun, but instead are influenced by other factors, such as internal structure or cosmic radiation? If so, K1-ATLAS may not be an anomaly, but a sign that we need to refine our understanding of how these icy bodies break apart and behave over time. The discovery of K1-ATLAS and 3I-ATLAS within such a short time span has raised an intriguing possibility. Are these two objects related? At first glance, their unusual behaviors, fragments, motion anomalies, and chemical signatures might seem like coincidences, but when viewed together, the timing of their arrivals, as well as the strange behaviors they both exhibit, raises important questions. Could K1 and 3I-ATLAS be parts of the same cosmic puzzle? Could they be fragments of a single, larger object that was once whole, only to disintegrate far from the Sun, scattering debris across the galaxy? The similarities between these two objects are too striking to ignore. Both were discovered by the same Atlas survey network, both showed unusual motion and fragmentation patterns, and both displayed chemical compositions that differ significantly from typical solar system comets. While K1 was initially classified as a long-period comet from the Oort cloud, its chemical and structural anomalies suggest that it might be something far more unusual, possibly even an interstellar visitor like 3I-ATLAS. This theory of a shared origin is supported by the data, though it remains speculative. If K1 and 3I-ATLAS are indeed fragments of the same object, their similar chemical signatures and strange behaviors could point to a larger cosmic event that occurred far before either fragment entered our detection range. The question then becomes, how many more fragments of this ancient object might be out there, waiting to be discovered? Are we just beginning to see the first pieces of a much larger debris field that stretches across time and space? The peculiar way in which K1 Atlas fragmented into distinct, organized pieces, rather than a chaotic cloud of debris, raises important questions about the internal structure of comets and the forces that govern their behavior. It is not uncommon for comets to break apart when subjected to the extreme conditions of perihelion, but the organization of the fragments in K1's case is exceptional. The comet's fragmentation pattern, where pieces separated along a linear axis, suggests that the nucleus of K1 may have had a complex internal structure, one that caused it to break apart in an orderly manner.
This behavior challenges the traditional view of comets as loose aggregates of ice and dust, held together by weak gravitational forces. If K1 Atlas's nucleus was composed of discrete, layered material that broke apart along pre-existing planes of weakness, this could mean that comets, like K1, may have much more complex internal structures than previously believed. The fragmentation pattern observed in K1 suggests a level of organization that goes beyond simple mechanical failure. Understanding the forces that caused K1's fragmentation is critical to our understanding of cometary physics. Could the comet's rotation rate, its internal pressure, or even the chemical composition of its nucleus have played a role in shaping the way it broke apart? These questions remain open, and the data from K1's fragmentation could be the key to unlocking new insights into the physical processes that govern the behavior of comets. In addition to the usual forces exerted by the Sun, K1 Atlas's behavior suggests that cosmic radiation could also play a significant role in shaping the structure of comets. As interstellar objects travel through space, they are constantly bombarded by cosmic rays, radiation from distant stars, and even cosmic dust. Over time, this radiation can alter the chemical composition of a comet's surface, making it more fragile and prone to breaking apart under stress. K1's carbon depletion and the lack of typical carbon emissions could be evidence of such processes. If K1's nucleus had been exposed to high levels of cosmic radiation over millions of years, this could explain why its chemistry differs from typical solar system comets. Radiation-induced changes to the volatile content of the comet could have made it more prone to fragmentation, with layers of volatile-rich ice sublimating faster than expected under solar heating. If this hypothesis is correct, it would have profound implications for how we understand cometary chemistry and behavior. It suggests that comets from interstellar space might be fundamentally different from those that originate in our solar system, shaped by the harsh conditions of cosmic radiation. If K1 is indeed an interstellar object, its unusual behavior could be the result of these long-term environmental effects. The increasing number of interstellar objects entering our solar system presents an exciting opportunity for astronomers to search for patterns in the distribution and behavior of these objects. If K1 Atlas and 3IATLAS are part of a larger stream of interstellar debris, we might begin to detect similar objects in the future. These objects could share certain characteristics: unusual motion, fragmentation patterns, and chemical anomalies that would allow scientists to identify them as part of the same cosmic stream. The idea of interstellar debris streams is still speculative, but it provides a compelling framework for understanding the nature of these objects.
If large interstellar bodies break apart before they enter our detection range, their fragments could spread across vast distances, arriving in our solar system at different times. As we continue to monitor the skies and improve our detection methods, we may begin to see a pattern emerge, one that suggests that objects like K1 Atlas and 3I Atlas are not rare exceptions, but rather part of a larger, ongoing phenomenon. The discovery of these streams would revolutionize our understanding of interstellar material and its role in shaping the solar system. It would suggest that our solar system is not a closed system, isolated from the rest of the galaxy, but rather a dynamic part of a larger cosmic network, constantly interacting with the material that flows through the galaxy. Looking ahead, the study of interstellar objects like K1-ATLAS, 3IATLAS, and others will be crucial in expanding our understanding of the universe. As our technology improves and we gain more experience in tracking and analyzing these objects, we will begin to answer the fundamental questions that have been raised by their discovery. Future space missions may allow us to send probes to these objects, collecting samples and studying them up close. These missions could provide the definitive answers about the origins of interstellar objects and the role they play in shaping our solar system. Until then, astronomers will continue to monitor the skies, gathering data and refining their models of how these objects behave and how they fit into the broader picture of cosmic dynamics. The study of interstellar objects is just beginning, and the discoveries we make in the coming years will undoubtedly reshape our understanding of the universe. As our technology improves and we gain more experience in tracking and analyzing these objects, we will begin to answer the fundamental questions that have been raised by their discovery. The discoveries of the past few years have opened a new chapter in astronomical research, and the questions raised by K1 and 3IATLAS are just the beginning. As our technology improves and our understanding deepens, we will continue to explore the unknown, unveiling the secrets of the universe, one discovery at a time. The study of interstellar objects such as K1-ATLAS and 3IATLAS continues to reveal fascinating complexities about the material that exists beyond our solar system.
While much of the focus in recent years has been on the behavior and origins of these objects, an equally important question arises. What exactly is interstellar material, and how does it behave under the unique conditions of space travel? Interstellar objects like comets, asteroids, and even larger fragments are often made up of a variety of materials, ranging from volatile ices and gases to rocky and metal-rich compositions. Some of the most intriguing findings about K1 and 3IATLAS are related to the chemical anomalies observed within their cores. These objects appear to contain a mixture of elements and compounds that are less commonly found in comets originating from our own solar system. This raises the possibility that interstellar material, especially fragments like K1, could contain components not present in the familiar bodies of our solar system, providing us with rare opportunities to study cosmic processes that are entirely foreign to us. One of the most compelling aspects of these interstellar objects is the chance they provide to learn about the environments of other star systems. The chemical composition of these objects, along with their motion, could offer valuable clues about the conditions of their birth. How did they form? What type of stellar environments did they come from? Were they subjected to radiation or gravitational forces that differed significantly from the conditions in the solar system? The answers to these questions could help scientists refine models of planetary formation, as well as deepen our understanding of how material behaves in interstellar space. As more objects like K1 and 3IATLAS are discovered, astronomers will likely begin to detect additional anomalies that will challenge our traditional definitions of what these objects are and how they behave. The complexity of interstellar material is likely much greater than we have imagined, and these objects are the first tangible evidence we have of this complexity. They are a gateway into the unknown, one that holds the promise of uncovering new and surprising aspects of our galaxy. Gravitational interactions have always been a critical part of our understanding of how celestial bodies move through space. However,
The arrival of interstellar objects like K1 and 3IATLAS suggests that gravitational forces play an even more significant role in shaping these objects than previously thought. These objects don't just pass through the solar system, they're altered by the gravity of our sun, planets, and other stellar bodies. K1 Atlas, for example, did not follow a simple, predictable orbit through the solar system. Instead, its motion exhibited slight but measurable anomalies that suggested gravitational forces beyond those exerted by the sun alone. This type of behavior isn't unique to K1. Other interstellar objects, such as 1I Oumuamua and 2I Borisov, have also exhibited unexpected motion that couldn't be explained by gravitational forces alone.
The question then arises, what forces, other than those traditionally considered, might be influencing these objects? One possibility is that interstellar objects could be interacting with the gravitational fields of planets or even distant stars. As they pass through our solar system, they could be nudged by the gravitational influence of giant planets like Jupiter, which could cause subtle changes in their trajectory. In some cases, these interactions could even alter the object's velocities, increasing or decreasing their speed as they make their way through the solar system. This idea opens up a new layer of complexity in understanding the movement of interstellar objects. As we continue to track these visitors, it will be crucial to take into account the gravitational influence of all the bodies in the solar system, not just the Sun, when predicting their paths. With more data on how these objects interact with the gravitational fields of different planets, we could gain deeper insights into the mechanics of space travel on interstellar scales. The discovery of K1 Atlas and 3I Atlas is not just a breakthrough for cometary science, it also contributes to a broader understanding of stellar and planetary system dynamics. These interstellar objects raise important questions about the evolution of our solar system and the interactions between different stellar bodies. One of the key implications of these discoveries is that the solar system may not be as isolated as once believed. For years, scientists assumed that our solar system was relatively self-contained, a separate entity within the vastness of space. However, as we learn more about interstellar objects, we begin to realize that our solar system is just one part of a much larger cosmic network. The idea that interstellar material is frequently passing through our solar system suggests that we are not living in an isolated bubble, but are constantly interacting with other stars and their planetary systems. The movement of interstellar objects like K1 and 3I Atlas suggests that our solar system is part of a larger dynamic environment, constantly being influenced by neighboring stars. These interactions could have significant implications for the evolution of our own planetary system. For example, interstellar objects could introduce new material into the solar system, potentially influencing the formation of planets, moons, and even life itself. Additionally, these interstellar visitors could be providing us with clues about how stars and planetary systems form, evolve, and interact with each other. As we learn more about how interstellar objects behave and interact with the solar system, we may gain a deeper understanding of how our own star system evolved and what forces have shaped it over the millennia.
While comets and asteroids have long been known to pose potential risks to planetary bodies, the arrival of interstellar objects adds an additional layer of complexity to our understanding of these risks. Unlike comets originating from the Oort cloud, interstellar objects like K1 Atlas and 3I Atlas do not follow predictable regular orbits. This means that their arrival is less foreseeable and potentially more dangerous. The behavior of these objects, particularly their unpredictable motion and fragmentation, suggests that we may need to refine our models of cosmic risk. While the likelihood of an interstellar object directly impacting Earth is small, the unpredictable nature of these objects makes it difficult to assess the full range of potential risks. As we track more interstellar objects, we will need to develop better ways to predict their paths, understand their behavior, and determine the possible consequences of their arrival. In this context, the study of K1 Atlas and similar objects becomes crucial not only for scientific exploration, but also for planetary defense.
Understanding how these objects behave, how they fragment, and how they interact with the solar system's gravitational forces will be key to developing effective strategies for mitigating any potential risks. The growing number of interstellar objects entering our solar system presents an exciting opportunity for exploration. While current technology has allowed us to track and observe these objects from afar, the next step in interstellar object research is to send probes to these objects, collecting samples and studying them up close. Missions like the New Horizons probe, which visited Pluto and its moons in 2015, have already shown us how much we can learn from close-up observations of distant objects. By sending similar probes to interstellar objects, we could gain invaluable insights into their composition, structure, and origin. These missions could unlock the secrets of how interstellar bodies form, how they interact with their parent star systems, and how they behave as they travel through space. Although sending probes to interstellar objects presents significant technical challenges, such as the vast distances involved and the need for advanced propulsion systems, these missions represent the future of space exploration. As technology continues to evolve, it's likely that future generations of scientists and engineers will find ways to reach these objects and bring back data that could revolutionize our understanding of the cosmos. The study of interstellar objects, from K1-ATLAS to 3I-ATLAS, is opening a new frontier in our understanding of the universe. These objects are challenging our current models of cometary science, planetary formation, and cosmic dynamics. As we continue to track, study, and explore these strange visitors from beyond our solar system, we are learning that the universe is far more interconnected and dynamic than we ever realized.
The discoveries of the past few years have changed the way we view our place in the galaxy, revealing that our solar system is not isolated but a part of a larger, more complex cosmic network. The study of interstellar objects is just beginning, and with each new discovery, we are pushed to expand the limits of our knowledge. In the future, these objects may hold the key to unlocking the mysteries of planetary systems, the evolution of the galaxy, and even the origins of life itself. As we continue to explore the cosmos, we are reminded that the universe is full of surprises. Every new discovery brings new questions, new challenges, and new opportunities to learn about the nature of existence. The journey of discovery is just beginning, and who knows what we will uncover next. As the study of K1-ATLAS and 3I-ATLAS progresses, one of the most exciting aspects of this field is the potential for new missions dedicated to exploring interstellar objects. Currently, our ability to study these objects is limited to remote observations through telescopes and spectrometers. However, there is a growing push within the scientific community to send dedicated probes to these objects in order to gain a more detailed understanding of their composition, behavior, and potential origin. Missions to interstellar objects will present significant technical challenges, but with advancements in space exploration technology, these challenges are not insurmountable. The prospect of sending spacecraft to intercept interstellar objects opens up possibilities that were once thought to be beyond our reach. For instance, the success of the New Horizons mission, which successfully passed by Pluto in 2015 and continues to send valuable data from the Kuiper Belt, shows us that with the right technology and planning, reaching distant objects is achievable. A dedicated mission to a comet or interstellar object would likely involve sending a probe equipped with high-resolution cameras, spectrometers, and perhaps even sampling instruments to study the object's composition up close. Such a mission could provide us with a wealth of data about the material that makes up these distant visitors, revealing how they formed and how they interact with the space environment. The discovery of interstellar objects like K1-ATLAS and 3I-ATLAS forces us to rethink our view of the solar system itself. For centuries, we've regarded the solar system as a relatively closed system, isolated from the rest of the galaxy by vast stretches of interstellar space.
However, the increasing frequency of interstellar objects passing through our solar system suggests that our solar system may not be as isolated as once thought. The solar system is not a static, closed system, but rather a dynamic part of the larger galactic environment. Interstellar objects serve as reminders that our solar system is constantly interacting with the material that exists in the surrounding galactic space. These interactions have important implications for the way we think about the evolution of the solar system and how it has been shaped by external forces. For instance, if interstellar objects like K1 and 3I/ATLAS are part of a larger debris field, this means that our solar system is not immune to the effects of the cosmic material that flows through it. These objects could introduce new materials into the solar system, influencing the formation of planets, moons, and other celestial bodies. They might even impact the development of life itself, as the building blocks of life could potentially be transported from one star system to another. The study of interstellar objects will help us understand the extent to which our solar system has been shaped by external forces over the course of its history. As we continue to observe these objects and refine our understanding of their behavior, we may begin to see a clearer picture of how cosmic events and interactions have influenced the formation of our planetary system.
One of the most significant implications of the study of K1-ATLAS and 3I-ATLAS is how these objects might reveal cosmic events that shape the solar system. As interstellar objects enter our solar system, they bring with them the possibility of new material and new forces at play. These objects might not just be passive visitors, but active participants in the ongoing evolution of the solar system. For example, the interaction between interstellar objects and the Sun's gravitational field could provide insights into the way solar systems form and evolve. As interstellar objects pass through the solar system, they could experience forces that alter their motion, potentially even influencing the trajectory of planets or other celestial bodies. These interactions could have significant implications for planetary formation theories. If the solar system has been subject to the gravitational influence of passing interstellar objects, it may suggest that the formation of planets and other bodies in the solar system is not entirely a localized process, but rather one influenced by the larger cosmic environment. Moreover, the study of these objects could reveal how other star systems evolve. Understanding how interstellar objects behave as they pass through different solar systems will provide important clues about the conditions that allow stars and planets to form. The arrival of interstellar objects has also fueled speculation about the potential for life beyond our solar system. The idea that interstellar material could enter the solar system has prompted researchers to consider whether such objects could carry the building blocks of life. If these objects are indeed fragments of larger planetary bodies, they may contain organic compounds or other molecules that are essential to the formation of life. This raises an exciting possibility. Could interstellar material be responsible for the spread of life across the galaxy? The idea of panspermia, the theory that life, or the building blocks of life, can be transported between planets and star systems, has been discussed for many years. Interstellar objects like K1-ATLAS and 3I-ATLAS could potentially be carriers of life, either in the form of microbial life or the chemical ingredients needed to support it. While this theory remains speculative, it provides an intriguing framework for understanding how life might spread across the galaxy. The discovery of interstellar objects is not only reshaping our understanding of the cosmos, but also opening new possibilities for the search for life beyond Earth. The exploration of interstellar objects like K1-ATLAS and 3I-ATLAS has revealed many surprises and challenges. These objects have forced scientists to rethink their assumptions about the nature of comets, planetary formation, and the dynamics of our solar system. They have expanded our view of the universe, showing that our solar system is not an isolated bubble, but part of a larger interconnected cosmic environment. As we continue to study these objects, we will undoubtedly encounter more mysteries that challenge our understanding. The future of interstellar object research holds great promise, with new technologies and missions on the horizon that will allow us to explore these objects up close. The discoveries made in the coming years will shape our understanding of the universe and may even lead to new insights about the origins of life itself. The study of interstellar objects is just beginning, and the discoveries we make today will lay the groundwork for the next generation of explorers. The universe is vast, and as we continue to push the boundaries of our knowledge, we will uncover new and exciting mysteries that will continue to inspire wonder and curiosity. As we move forward with the study of interstellar objects like K1-ATLAS and 3I-ATLAS, it is clear that these objects are far more than just cosmic curiosities. They are windows into the past, into the history of the galaxy itself. The objects we are seeing today are the remnants of processes that took place long before our solar system was even formed, and by studying them, we can gain insights into the formation and evolution of stars, planets, and even the building blocks of life. In many ways, interstellar objects serve as messengers from distant star systems, bringing with them clues about the cosmic processes that shaped their formation. These objects, while seemingly small and fleeting in the grand scale of the universe, carry with them a wealth of information that is invaluable for our understanding of the universe's history. Whether these objects are fragments of larger, destroyed bodies or survivors of distant planetary systems, their study offers us a unique opportunity to learn about the wider galactic environment. One of the most important lessons we've learned from K1-ATLAS, 3I-ATLAS, and other interstellar objects is the realization that the universe is far more interconnected than we once thought. These objects do not come to us in isolation. They are part of a vast network of cosmic material that moves and interacts throughout the galaxy. This realization opens up new avenues of exploration, suggesting that we are not passive observers of the cosmos, but active participants in a much larger cosmic system.
Instead, the arrival of interstellar objects like K1-ATLAS and 3I-ATLAS forces us to rethink how we understand the role of gravity in shaping the movement of celestial objects. While these objects may be initially influenced by the sun's gravity, their motion can also be altered by the gravitational forces of nearby planets, moons, and even other stars. The gravitational pull of large bodies like Jupiter can significantly alter the trajectory of an interstellar object, causing it to change course in ways that are not immediately predictable. For example, the slight accelerations and motion anomalies observed in K1-ATLAS and 3I-ATLAS might be the result of gravitational interactions with other objects in our solar system. These interactions could cause the objects to experience forces that push them in unexpected directions. The gravitational influence of planets like Jupiter, with its immense mass, could have been enough to alter the trajectories of these objects as they pass through our solar system. Understanding the role of gravity in these interactions is crucial for developing more accurate models of interstellar object motion. As we continue to track more interstellar objects and observe their movements, we will gain a clearer picture of how these objects are influenced by the gravitational forces within our solar system. This knowledge will be key in predicting the paths of future interstellar visitors. The study of interstellar objects like K1-ATLAS and 3I-ATLAS also provides valuable insights into the dynamic processes that shape our solar system and its evolution. While these objects might seem like distant visitors, their presence in our solar system is not without consequence. Over time, the arrival of interstellar objects could influence the evolution of planetary bodies, including Earth. For example, the collision of an interstellar object with a planet could have profound consequences for the planet's surface and atmosphere. In the past, impacts from comets and asteroids have been responsible for major extinction events on Earth, including the famous impact that is believed to have contributed to the extinction of the dinosaurs. While the likelihood of a direct collision with an interstellar object is low, the possibility exists, and scientists are beginning to explore the potential risks these objects pose. Beyond the risk of direct impact, interstellar objects might also introduce new material into the solar system. This could affect the chemical composition of planets and moons, potentially influencing the conditions necessary for life to thrive. For example, if an interstellar object carries organic molecules or water, it could contribute to the development of life on planets like Earth. One of the most exciting prospects for studying interstellar objects is the possibility that they could carry the seeds of life.
The theory of panspermia, which suggests that life, or the building blocks of life, could be transported between planets and star systems, has been a topic of scientific debate for many years. The discovery of objects like K1-ATLAS and 3I-ATLAS, with their unusual chemical compositions, has reignited interest in this theory. While it is still highly speculative, the idea that interstellar objects might carry the building blocks of life is both tantalizing and profound. If these objects are remnants of ancient planetary systems, they could contain organic compounds, amino acids, or even microbial life that have traveled across the galaxy from one star system to another. If this material has the potential to seed life on planets like Earth, it could revolutionize our understanding of life's origins. The study of interstellar objects is just beginning, and scientists are now more eager than ever to examine these objects for signs of life or organic material. Advances in space exploration technology, such as the development of probes capable of landing on these objects and collecting samples, could provide the key to unlocking this mystery. The discovery of life, or the building blocks of life in an interstellar object, would be one of the most significant scientific breakthroughs in history. The story of K1-ATLAS and 3I-ATLAS also serves as a reminder of the vast distances and timescales involved in the life of interstellar objects. These objects are not just fleeting visitors to our solar system. They are travelers on an extraordinary journey that spans thousands, if not millions of years. The sheer scale of their travels highlights the incredible distances between stars and the vastness of the galaxy. Interstellar objects like K1 and 3I-ATLAS have likely traveled across immense distances, moving from one star system to another. Their paths have been shaped by the gravitational forces of other stars, black holes, and the cosmic material they encounter along the way. Their arrival in our solar system is a rare event, one that provides us with a glimpse into the broader dynamics of the galaxy. As these objects pass through the solar system, they bring with them stories of the distant regions of space they have traveled. These stories, told through the object's chemical composition, motion, and behavior, offer a unique opportunity to learn about the environments of other star systems and the forces that shape them. The discoveries of K1-ATLAS, 3I-ATLAS, and other interstellar objects have ushered in a new era of exploration. These objects challenge our understanding of the universe and force us to confront the limits of our knowledge. They are a reminder that the cosmos is vast, filled with mysteries waiting to be uncovered. As we continue to study these interstellar visitors, we will undoubtedly encounter more surprises that push the boundaries of our understanding.
The questions they raise will lead to new discoveries, and the knowledge we gain will shape our view of the cosmos for generations to come. In the future, as technology advances and new missions are launched, we may find that the study of interstellar objects is not just about tracking these visitors, but about exploring the very fabric of the universe itself. The journey of discovery is far from over, and the universe is full of secrets waiting to be uncovered.